Thank you so much for the invitation. I'm really excited to be here and to speak with this very diverse group. And I want to preface my talk by saying it's always hard to gauge an audience, but in this case I think there might be even a wider range than typical. And so my aim is to try to not assume too much background knowledge, so some of this will be review and seem very, very basic to many of you, and I apologize for that. But hopefully there's also some original and provocative stuff in here, enough for some discussion. So I look forward to hearing your thoughts about these topics. So I've been speaking on the issue of replicability and replication in psychology for a while, and it's really hard to know what to call this phenomenon, this movement, whatever it is. And lately I've borrowed a term from economics and started calling it the credibility revolution. And I like this phrase a lot better than the replicability crisis or other things, because I think that this movement, or whatever you want to call it, maybe the open science movement, it's not just about openness. I think it's about more than just openness. So I don't use the phrase open science movement to describe this whole thing. I don't like the phrase replicability crisis because it's about more than just whether things replicate or not. And I also have some issues with the word crisis, although I slip into using it sometimes, as you'll see in this talk. But I think it's really the common goal here is credibility. That what a lot of these movements, a lot of these discussions have in common is to try to increase credibility of science. And I'm going to talk from the perspective of psychology, but I really think this is a concern that cuts across all of sciences, and that some of the problems raised and the problems identified aren't specific to psychology. Psychology has been at the eye of the storm for a number of reasons, but I don't think any field is completely safe from these concerns. So today I'm going to start by talking about some values and norms in science, because I think it's best to start with some common ground. And as I've been thinking and teaching about these issues, I keep coming back to what is science about, what makes science different from other ways of knowing, which seems like an easy question, but is actually pretty hard. Then I'll do a little bit of stats review just to lay the groundwork for some of the problems that we've identified in psychology and beyond, and I will try to refrain from calling it a crisis. I don't know if that's accurate, but describing some of the problems that have been identified and then talking about some of the proposed solutions. So I'm going to start with this issue of values and norms. A lot of the discussion about open science and replicability has focused a lot on pragmatic issues, like we can use R and we can use R Markdown, we can have reproducible workflows and so on. And I think what's missing from a lot of that discussion is kind of going back to the question of what do we value in science, what are our principles, what are our ethics, and so on. There's very little discussion of that. And when I was being trained in grad school, the only ethics I really got was about treating participants right and getting informed consent and so on. But I actually think we should be thinking about why we care about openness and reproducibility and so on. And I've only really found some of that language and writing recently. It's not something I was trained in or came across in my training. But especially I teach the undergraduate research methods course in psychology at UC Davis. And one of the questions we start with is what makes science different from other ways of knowing? And a related question that I ask myself is, when we're training scientists, what are you signing up for when you're signing up for science? What are some of the core values and norms that you're agreeing to when you become a scientist? And the set of answers that I found most compelling is Merton's norms. So he was a sociologist of science writing in the 1940s. And so I'll describe his 4 norms that he proposed and then talk a little bit about whether we live up to these ideals. And we can talk about whether or not this is descriptive of what scientists do or it's more aspirational. But I think it helps to lay out whether there are some general things that we all agree on as scientists that we should value or we should aspire to. So one is the norm of universalism. And this norm states that the validity of a scientific claim does not depend on who's making it. So we should ignore who's making the claim when we're evaluating the validity of the claim. That means there should be no hierarchy and status should not matter in the context of evaluating the validity of a scientific claim. Obviously, hierarchies exist and status matters when deciding who should be a department chair or who should get an award or things like that. We're never going to completely get rid of status and hierarchy. But when we're in the context of evaluating the validity of a scientific claim, we should not take into account who's speaking or who's making the claim. The second norm is communality. It used to be called communism and then was renamed. And this norm says that the findings of science belong to everyone. They're not private property. Open communication is key, and there should be no secrecy in science. And this is maybe the closest to the spirit of the open science movement. The third norm is disinterestedness, which I think we can all agree is more of an aspirational norm. This is very, very hard for humans to live up to. But the idea is that scientists should be focused on finding the truth, not on their own success. And so self-interest should not be a determinant in how we decide the validity of scientific claims. You should report whatever you find, even if it makes you look bad. And then I think this goes hand in hand with the fourth norm, which is organized skepticism, which is that we don't take things at face value. We're expected to verify each other's claims, so we should expect others to want to verify our claims. And again, even if this goes against the self-interest of the person making the claim. And along with that, nothing is sacred. That even if we have certain values outside of science, political values and so on, we can't treat scientific claims as part of that system. We need to be allowed to challenge any scientific claim. Now, this might be a little bit idealistic, and I have some friends in philosophy of science who think that scientists do have a responsibility to think about the implications of their claims for politics and social causes and so on. So I think we could debate that, but at least there should be some room for challenging even things that we wish were true. There was a study in 2007 looking at whether scientists endorse these norms, and so they didn't use these words exactly, but they described the norms in colloquial language and asked scientists, do you subscribe to these norms? Do you act in accordance with these norms? And do you think your colleagues act in accordance with these norms? And they compare the norms to the counter norms. So the counter norm, for example, for communality would be secrecy. The counter norm for disinterestedness would be self-interestedness. And they surveyed people who had been granted NIH grants in a certain period. And the study was published in 2007. These are US-based scientists. So the top bars, the gray bar, the majority of respondents, these are their self-reports of whether they subscribe to the norm. So the vast majority of scientists surveyed, mid-career and early career scientists, say that they do subscribe to the norm. The black part is the people who subscribe to the counter norm. So very few scientists say that they subscribe to the counter norm. And then when asked about their own behavior, most said that their behavior is in line with the norms. Few said that their behavior is in line with the counter norms. And then when asked about other scientists' behavior, that flipped, right? Most people describe their peers' behavior as being consistent with the counter norms rather than with the norms. So I think we can all relate to this, that we might aspire to be disinterested or to value skepticism or communality, but it's hard when it comes to our own or others' behavior to really live up to that. But I think for me, this provides a grounding when asking myself, what should we as scientists do? What should we value? What should the incentive structure be? I come back to Merton's norms. I believe that they're a pretty good set of guidelines for how science should operate, but I'd love to hear other thoughts about this. I haven't come across too many other models of what the core values are in science. So one of the themes that runs across many of these norms is the issue of transparency. And this has been a big part of the discussion about replicability and open science and so on. And I think that one of the main arguments for transparency is just that it's a value in itself, that what it is to do science is to be transparent and open. And this was expressed well in a paper by Lupia and Ellman, where they wrote that the credibility of scientific claims comes in part from the fact that their meaning is at a minimum available for other scholars to rigorously evaluate. Such open access to the origins of others' claims is the hallmark of scientific ways of knowing. Accordingly, when social scientists fail to document their assumptions, decisions, and actions, it limits others' ability to understand the meaning of scientists' claims. So they're arguing that what it is to do science is to make your claims verifiable to others. And this is not new. This goes back at least to the motto of the Royal Society of Science, which is the oldest still existing scientific society. And their motto is take no one's word, or as I like to paraphrase, science means never having to say, trust me. Now, I don't mean that literally. I do think trust is important in science, but I think that we should try to eliminate or minimize the role of trust whenever we can. So when we have the option of either saying trust me or saying, here, check for yourself, we should opt for the latter. So we should not say trust me when there's an alternative, when we can make things transparent and verifiable to others. And that's really, I think, one of the, if not the most fundamental thing that makes science different from other kinds of claims of knowledge. So in thinking about why we should do science in this open and reproducible way, I think the first advantage is that you could argue that it's what makes science science, that if we give up transparency, we're giving up the game and we're no longer distinguishable from other ways of knowing. So that's kind of an ethical or moral argument for transparency in science. And in thinking about this issue, I came up with another argument that's more pragmatic. And I came up with this argument when I heard about Akerlof's paper, The Market for Lemons, Quality, Uncertainty, and the Market Mechanism. So he's an economist. And he wasn't writing about open science. He was writing about what happens in markets where there's information asymmetry. So when the buyer knows a lot more than the seller, and he used the used car market as an analogy or as an example for this kind of market. So in the used car market, the seller might know that the car has been in accidents or that the timing belt is about to snap or things like that, and they may or may not have to disclose that information to the buyer. And he says that what happens in those markets is that the buyer has quality uncertainty. They know that they lack information. It's kind of like known unknowns, right? So when the buyer is in a position where they know that they can't tell apart high quality products from low quality products, they know there's information they lack, then they start to lose trust in the market and refuse to invest in any products because they know that they lack information. So he was talking about how this asymmetry in information can lead to a lack of trust. And as I was reading this, I was thinking they're kind of in the same situation with research. When we want to evaluate research, we know that we don't have all the information. We know that the researchers have a lot more knowledge about what went into the scientific claim that they're making than we as consumers of that research, as readers, reviewers, editors, trying to evaluate the research. We know there's stuff we don't know. We know there's history we don't know. We know there's details that weren't in the report, et cetera. And so I wrote a paper arguing that if we let this asymmetry get too big, if the difference between what, in this case, author or researcher knows, that's an analogy with used cars, they're in the position of the seller, and what the reader, reviewer, consumer, et cetera, knows, if we let that asymmetry get too big, consumers and readers will know that they lack critical information to evaluating the validity of the claim, and they might eventually refuse to buy any of the claims because they know that they can't tell the rigorous claims apart from the more flimsy ones. So it's in our interest, even if you don't buy the moral argument for transparency, you could take a more pragmatic approach and say, if we want people to trust science, we need to give people the information they need. We need to let them look under the hood, let them kick the tires, let them see everything that went into the claims that we're making. And I make the case in the paper that we wouldn't accept, when buying a used car, we wouldn't tolerate a seller saying, no, you can't look under the hood, or no, you can't see what the history of the car, et cetera. And so we shouldn't tolerate that in science either. It should be completely normal to ask for the information you need in order to evaluate the validity of the scientific claim. So that leads to my second argument for open science, which is that if we don't become open and share and let others verify our scientific claims, then it's possible that we'll lose the trust of others. So it's a more pragmatic argument. A third reason I think it's important to be open and transparent and to subscribe to Merton's norms is that if you ask people, well, what's one unique characteristic, a defining characteristic of science? I think many people will say, well, science is self-correcting. Unlike other kinds of knowledge, if there's an error in science, there's a good chance that we'll root it out and fix it and correct. And I think that's something that allows a lot of us to sleep better at night, right? We have this fundamental belief in the self-correcting nature of science. But I think it's important that we ask ourselves, what makes science self-correcting? What's built into the system that allows for self-correction and that ensures self-correction? And here's a tweet from James Heathers where he makes a point that it's not necessarily inherently self-correcting. There's no magical guarantee that science will be self-correcting. So if we wanted to design a system with the greatest chance of self-correction, what would we want that system to have? And then I keep coming back to Merton's norms once again. So self-correction requires universalism. It requires the idea that anyone can challenge someone else's claims. If we have too much hierarchy and if we evaluate scientific claims based on status, then if you have enough status, no one can challenge you, and your claims that are wrong won't get corrected. Self-correction also requires transparency. It's very hard to detect errors and correct them if there's information missing that's kept secret. Self-correction requires disinterestedness. We need to value the truth above any individual person's self-interest or reputation. So if correcting a claim means that it'll have a negative side effect for a person's ability to succeed or make money or that kind of thing, we need to put the truth ahead of that. And self-correction requires skepticism. It needs to be a valuable part of the scientific community to point out errors and fix things. We need to make this an activity that's rewarded or at least not punished, and not immediately jump to conclusions about people's motives, right? If we want science to be self-correcting, we have to accept that some people are going to have to do that self-correction. or that correction of others. So a third argument for open science is that I think it's necessary for self-correction. If we want to continue getting credit for being self-correcting, unlike other sources of knowledge, then I think we need to be committed to these values. Okay, so now shifting gears a little bit, I'm going to start talking a little bit about statistical practices, and I'm going to start from the very basics. So again, I apologize, this is a review for many people. So just as a review, in null hypothesis significance testing, which is the framework I'll be talking about today, but a lot of the arguments I'm going to be making would apply just as much in other frameworks, including Bayesian frameworks, but not some of the specific points. So in null hypothesis significance testing, we talk about two kinds of errors, type 1 errors and type 2 errors. And so I'm going to be talking about how often do we make these kinds of errors in this null hypothesis significance testing framework, and I'm going to way oversimplify. So what we do when we're doing null hypothesis significance testing is we run a study and we try to decide if we found no effect or if we found an effect, and we use an alpha threshold, what our p-value needs to be lower than in order to conclude that we got an effect. So based on the results of our study, we decide if we're in the top row or the bottom row. If we get a non-significant result, we decide we're in the top row. If we get a significant result, we decide we're in the bottom row. And that's all we can really know in this framework is which row we're in. But there's also a true state of the world, which we can't know, and those are the columns here. So again, to oversimplify, either there's no effect, the left column, or there is an effect, the right column. And so we can cross the columns and the rows and get the different possible outcomes. So if we don't detect an effect, and we happen to be in the left column where there's really no effect, that's, maybe not happy news because we can't publish our results, so we didn't support our prediction, but at least we're making the correct conclusion. And the maybe more desirable outcome is when we detect an effect, and we hope that when that's the case, when we're in the bottom row, we hope that means we're in the right column, and we've gotten a hit. We've detected a real effect. And then the other two possibilities are the two kinds of errors. So false positives, or type 1 errors, and false negatives, or type 2 errors. One of the guarantees that null hypothesis significance testing is supposed to give us is that when we set our alpha, when we set what the p-value needs to be lower than in order to be significant, we control the type 1 error rate when we're in the left column. So what alpha does is it says by setting alpha to 5%, we're committing to this idea that in the long run, when we're testing effects, when our predictions are wrong and there actually is no effect, 5% of the time we'll end up detecting an effect or thinking that we detected an effect as a false positive, and 95% of the time we won't detect an effect. So that is one kind of reassurance, maybe one of the benefits of this approach, null hypothesis significance testing, but it rests on a couple of assumptions. One is that we're following the rules of null hypothesis significance testing, and I'll get into those in a second. But the other is, that this 5% versus 95% is only true when we're in the left column, and we don't know when we're in the left column. People often misinterpret the 5% alpha level as meaning that out of all of our significant results, out of the bottom row, 5% are in the left column, false positives, and 95% are in the right column, hits. So out of all significant results, we can be sure that in the long run, only 5% will be false positives, and that's not the case. Even if you follow all the rules of null hypothesis significance testing, there is absolutely no guarantee that only 5% of your significant results will be false positives. So it's a common misconception about null hypothesis significance testing. So as I mentioned, one of the correct interpretation of the alpha, that when you're in the left column, when there's no effect, 5% of the time you'll reach a false positive conclusion, is only true if you follow the rules of null hypothesis significance testing. And I think the number one rule, or at least the number one rule that we forget about or violate of null hypothesis significance testing, is you make your prediction first and then you test it. Or at least you make a plan about what your key analysis is. You may not need to have a prediction, you may not have a directional prediction, but you at least have one key analysis that's planned ahead of time. You run that analysis, you get one p-value, and you interpret that one p-value. That is one of the conditions for p-values to be interpretable in the way that we want to interpret them, in the way that we do interpret them. And it's one of the conditions necessary for that 5% long-term error rate in the left column to be true. If we don't follow this rule, if we don't run one test, interpret one p-value, and make sure that test is pre-specified, then we don't even have that assurance of NHST that the long-term error rate in the left column will be 5% for false positives. So it's not a huge benefit of using NHST, that we can know that when we're in the left column, only 5% of the time we'll make a false positive, but it is one of the main reasons to use NHST, one of the main arguments that proponents of NHST use, But we don't even get that benefit if we don't follow this rule. Or another way to put this rule is hypotheses cannot be tested using the same data that were used to generate the hypotheses in the first place. We have to have a predetermined plan, if not a prediction, at least a question or a test in mind, and interpret only the p-value from that test. So when I talk about this, a lot of people say, yeah, well, I'm not too worried about that. People know what their key test is ahead of time. They have it in their mind, or even if they don't have it in their mind, the theory constrains it, right? Our theory predicts what the key effect should be in any given study, and I don't need to write it down ahead of time because anybody could tell from the theory what the key prediction would have been. Here, I don't want to speak for other fields, but I think that in psychology, at least, I don't think theories lead to such narrow, concrete predictions. I think if I describe a study to you and describe everything that was measured and manipulated and so on, it's not going to be super obvious what the key test was. There are often multiple possible hypotheses that could be tested with that design. This was expressed perhaps more eloquently on Andrew Gilman's blog recently. And he wasn't speaking about psychology specifically here, but he said, theories are so flexible that just about any comparison can be taken to be consistent with theory. Remember sociologist Jeremy Fries's characterization of some hypotheses as more vampirical than empirical, unable to be killed by mere evidence. So I think we need to be careful if we trust our theories to constrain and specify a clear key analysis ahead of time. I don't think many of us are there yet with our theories. Psychology is a very young science. Many social sciences are young sciences. That's all the more power to you if your theories are that specific, but I think we should be careful assuming that our theories really do constrain us in this way. So I think we want to be careful about whether we're breaking this rule of NHST that we have to have one pre-specified analysis ahead of time. So another advantage of using open science methods, which I'll describe in a second, is that if you use these methods like pre-registration, others can tell if you followed the rules of NHST and therefore can tell if your p-values are interpretable in the way that we always interpret them, at least in psychology. So in order to treat p less than 0.05 as the way that as meaning what we want it to mean, that in the long run we're keeping our false positive rate in that left column to 5%, we have to know that you had a specific analysis in mind. And open science can help you and others know that that's the case. Okay, so now I'm going to talk about what we've been doing that doesn't live up to these ideals and how we know that. So to go back to NHST, we have the false positive rate in the left column is 5% if that's what we use as our alpha and if we follow the rules of NHST. And in the right column, the percentages are dependent on our statistical power, right? So when there really is an effect, our chances of getting a hit are whatever our statistical power is. So if we design a study to have 80% statistical power, we're kind of guessing because we don't really know ahead of time. But if we're right, then we'll get a hit 80% of the time and a false negative the other 20% of the time. So again, that's if we follow the rules of null hypothesis significance testing. What happens when we don't follow the rules of null hypothesis significance testing, when we give ourselves more than one chance, we don't just run one analysis, or we run multiple studies and only report the ones that work and so on? What we're doing when we break those rules is we're pushing things down to the bottom row, right? We're making more things significant than would be if we had followed the rules. So that increases false positives. We're no longer sure that there's only a 5% type 1 error rate in this column. But you could argue, and I think that this is on some people's minds, that this has also helped us detect true effects. By giving ourselves multiple chances, by looking at it from several different angles, if there really is something there, we're more likely to find it. The problem with this argument is it's true. It reduces false negatives, right? We're less likely to think there's nothing there if we give ourselves many, many chances to find something there. But then even when we do get a hit, even when we do detect something, we detected it using shortcuts. So often we designed the study in a way that wasn't powerful enough to detect it. Then we used shortcuts, giving ourselves many chances to push that result from false negative to hit. But we weren't using the tools and procedures and designs necessary to reliably get that hit. So if someone else were to come along and think, oh, well, you got the result with this design, I'm going to copy your design and test it. If they don't break the rules of NHST, they just give themselves one chance, they're much more likely to land in the false negative space. So in a way, by pushing results down, we increase false positives, which is bad. And you could say, well, we reduce false negatives, which is good, but the problem is that those hits are not reproducible hits. They were achieved through shortcuts, which means if someone replicated your study exactly with the same sample size and so on, they probably wouldn't get that hit. So I really like Yuri Simonson's analogy of small telescopes and large telescopes. What's happening when you're using suboptimal design, say underpowered studies and so on, even if you're detecting a real phenomenon, you're not detecting it using reliable methods. So that's the equivalent of, let's say there's a star really, really far away, and you need a really powerful telescope to detect it. You use a much less powerful telescope, and you detect a star, but really it's a speck of dust on your lens because your telescope is not nearly powerful enough to detect that faraway star. You might happen to be right that there really is a star there, and your report based on the speck of dust is technically a true result. But if someone else uses the same kind of telescope to try to see that same star, they're unlikely to observe it because it wasn't a real observation that followed from your design. So I think there's a lot of concern about this method of pushing things to be significant, both for the concern about what it does to false positives and for even if your hypothesis and your prediction are right, if your tools weren't good enough to detect the effect, then it's not really a reliable source of knowledge. So what this does is it pushes things down, and we're still in a place where we don't know what proportion of the significant results are false positives and what proportion are hits. And we have this concern that maybe we're detecting things that our methods actually aren't even capable of detecting. Maybe we're using a small telescope and claiming to be detecting really far away stars, even if the predictions are right, they might not be obtained in a reliable and reproducible way. So what are these shortcuts we're using to push things from the top row down to the bottom row? And I'm describing in a very agentic sounding way that people are actively doing this. It's more that I think we didn't know the rules of NHST, we didn't know the consequences of breaking them, and many of us, I think, were taught these practices without understanding the consequences for these rates of false positives. So I'm going to again oversimplify how we can turn things from non-significant results into significant results. So first you run a study, you probably had a key question in mind, you run your analysis, did you get the effect you predicted? If so, great, you can publish it, or you can try at least. And if you didn't get the one effect that was the first most obvious thing to test from your data set, you can test other things. Maybe you had another outcome in there that you threw in there just out of curiosity, or you had another factor that you crossed with your key manipulation that you didn't really have hypotheses about, but you were curious if it might moderate the effect. So you can test those other questions. If one of those comes out, you can publish it. But often what you'll need to do in order to convince editors to publish it is pretend that that was what you predicted. So in psychology, we call that harking or hypothesizing after the results are known, which is where you design a study with one question in mind, you don't hit your target, you find a different significant result, not the one that you were originally most interested in. So you move your target and you say, yeah, that's what I was looking for all along. And in fact, in psychology, it was pretty common to train our students. I taught a chapter in my research methods course that told students to do this, to tell the story that's most interesting after you know the result, not the story you plan to tell from the beginning. That's boring, no one wants to hear about your wrong ideas. And this makes us look like really good shots, right? So that's one option to salvage your data set if your original prediction didn't pan out. And then another option is maybe none of the most immediately obvious analyses pan out. None of them are quite significant, but maybe some of them are close to significant. And you can get them to be significant by transforming a variable, dropping some outliers, adding a covariate, things like that. So if you can tweak the analysis, any of the analyses to become significant, you might be able to publish that, and that's what we call p-hacking. So p-hacking is tweaking an analysis or data collection or analysis. Adding more participants would be another way to p-hack in order to get a result to be below the threshold for significance. Here's some of the ways. These are from Leif Nelson's slides. Some ways to p-hack. These are kind of more focused on experimental psychology methods. So as a personality psychologist, it's easy to feel self-righteous and say, well, I don't have manipulations, so some of these things don't apply to me. There is a lot more ways than this to p-hack. So if you're not doing these things, it's not necessarily a guarantee that you're not p-hacking. Again, I'm using language that sounds very active, p-hacking as an active thing. I think it's just data analysis, right? But without following the rules of NHST. So if you don't plan one analysis ahead of time and stick to interpreting only that p-value, then you're potentially p-hacking without realizing it. There's a really nice demonstration on 538.com. Christia Schwanen had an article on these replicability issues, and she uses a real data set that you can go in and play with and test some hypotheses, and you can see how easy it is to p-hack. So, for example, let's say my research question is, I'm interested in whether the US economy is affected by whether Republicans or Democrats are in office. So I can define my terms. Which politicians do I want to include in deciding who's in office? Presidents, governors, senators, representatives. How do I want to measure economic performance? Employment? Maybe not, but inflation, GDP, stock prices. And then do I want to factor in power, so way more powerful political positions more heavily? Do I want to exclude recessions? So let's say this is my first attempt at operationalizing this question. This is my best guess at like what's the right analysis to test this question. And I run it, and these are the real data, and I get a p-value of 0.11, so my findings are not statistically significant. It says try defining your terms differently. So maybe I did that too hastily. Maybe I didn't really stop and think about how I should define who's in power. And now that I think about it, I should obviously exclude senators because their positions are not at all proportional to the population. So I can come up with a really good reason to exclude them. And maybe I shouldn't exclude recessions because recessions are part of the economy too. So I was silly to exclude them before. I'm not going to exclude them now. And maybe that is the right analysis, or maybe this is a better analysis than the first one. And I run that, and it's 0.03, and it's publishable. So p-hacking would be if I report this one and not the first one, or not any others that don't work out. And again, that doesn't mean that this analysis is the wrong one. It might very well be a better analysis and more justifiable than the first one. The problem is that my decision about which ones to report is dependent on the outcome. That's where we're violating not just the rules of NHST, but I think the rules of being honest researchers. And I don't mean to say that researchers who do this, including myself, I've p-hacked plenty. I don't think that it's a dispositional thing that we're dishonest. It's just I think it's very easy for us to trick ourselves and to rationalize that this is obviously the better analysis than the one that didn't work. So the paper that introduced this idea of p-hacking to psychology was a paper by Simmons, Nelson, and Simonson in 2011. And they p-hacked, except they did one thing differently than what p-hacking traditionally means. They actually gave us a chance to look at their p-hacking. So they reported what the p-hacked result looks like, and then they kind of lifted the curtain and showed what was actually going on behind it. But the p-hacked version of their result, they really ran this study with real participants and real data, and they showed that according to their birth dates, people were nearly a year and a half younger after listening to When I'm 64 rather than to Kalimba, p equals 0.04. So their point was to show that you can find evidence for a preposterous claim by using techniques that aren't detectable when you just report the result the way that it's acceptable to report results in many scientific journals. But that if we did know more about what went into that result, what they had to do, all the different things they tried, et cetera, it would be clear that this is a fluke, this is a false positive, right? They used content where it's obvious that it's a false positive, but the point is that other things that aren't as obviously false positives might have been produced using some of these same techniques. There's other surveys asking researchers about how often they've done these different p-hacking and harking practices and so on. There's a lot of debate about how prevalent these practices are, but I think there's many of us who know, I did them myself, I was taught them, and I taught other graduate students to do them. So I have little doubt that they're relatively prominent, but there's definitely some debate about that. And then finally, if harking and p-hacking don't work and you're stuck with only null results, then often you have no choice but to stick those results in the file drawer because many journals don't want to publish null results, or people are skeptical about the interpretability of null results. And there's some evidence that this is very common in psychology and beyond. So Finelli had a paper looking at what proportion of published studies report significant results as the key result. The y-axis goes from 0 to 100%, so this is 90%. So in recent years, 90 to 100% of published studies in psychology and psychiatry reported significant results as the key result. This might be worse in psychology than in other fields. So psychology is at the bottom of this graph, which shows the proportion of papers supporting the tested hypothesis, so basically the proportion of significant results, from 50% to 100%, so this is 90. So this is psychology and psychiatry down here, but right above us is materials science, which is a pretty different field, pharmacology, clinical medicine, biology and biochemistry, economics. At the top, but still at 70%, is space sciences, geosciences, environment, and ecology. So there are some differences across fields. I don't know how reliable those differences across fields would be if we took a different sample of journals or looked at different times. But there's plenty of fields where this is very common to only publish or almost only publish significant results. So when we don't follow the rules of NHST, we can get a lot of significant results, but probably, we're definitely increasing the rate of false positives relative to what we think our alpha is, and even some of the results that reflect true phenomena are detected with methods that probably can't reliably produce significant results. So we're probably seeing a lot of things that we think are real stars, but actually are specks of dust on our lens. Some might be in places where there really are stars, where there really are true effects, and some might be in places where there's nothing actually there. But how bad is this problem? So what is the proportion of false positives among the published literature, for example? So what we would really like to know is, since the published literature is basically this bottom row, what proportion of those results are false positives and what proportion of those results are hits? And Bayesians are very quick to say that that's what we really want to know, right? We don't really want to know the proportion of results in the left column that are false positives, correct predictions, because we don't know when we're in the left column. What we really want to know is the positive predictive value of significant results. So that is, if I'm in the bottom row, what are the chances that it's a hit versus a false positive? And there's just no mathematical way to deduce that. Unlike alpha, which is set, if we follow the rules of NHST, we know that 5% of the time when we're in the left column, we'll get a significant result. There is no formula for saying what proportion of significant results are true versus false positives. So how can we estimate this? Well, one idea was the reproducibility project in psychology. And the idea there was, the goal was to take a set of psychology studies published in top journals that's relatively representative of studies in those journals. Now, whether they achieved that goal, they didn't reproduce every study from the selected issues of the journals, so there's some selection bias there. So they took 100 studies published in 2008 in 3 of the top journals in social, personality, and cognitive psychology, and they attempted to replicate as many of them from those issues as possible. And out of those 100 original studies, 97% of them were significant. So this is p-values. This is the threshold for significance. So most of them were below 0.05. And then out of the replication studies, one way to quantify whether the replication was successful or not is whether the replication study result was significant by the same threshold. And then they talk about many other ways to estimate whether a replication study was successful or not. So that shifts the percentage above or below 37%. But there's no number, no interpretation of these 100 results that's really glowing, right? There's no way to analyze these data and come up with the conclusion that, close to 80%, which would be our goal if we had 80% power, that 80% of them were successful replications. So it might not be as bad as 37%, but it's probably pretty far from where we would like it to be. So this was one source of worry, that the false positive rate in psychology might be a lot higher than we should want it to be. And it was one of the earlier pieces of evidence. And since then, there have been many more replication studies, forensic analyses looking at distributions of p-values, for example, and other techniques to try to estimate how bad is the problem. They're all controversial. None of them is definitive. None of them is bulletproof. But the evidence seems to be pointing to this worry that there's probably a higher proportion of false positives in our literature than we should be comfortable with. And this has gotten a lot of media attention. A lot of it focused on psychology, but more and more this is broadening out to other sciences, especially other social sciences and medicine. But even things like cancer biology have come under attack, or under scrutiny rather. And this there was a survey done by Nature where they asked a group of scientists, mostly natural scientists, is there a reproducibility crisis in science? And many said yes, a significant crisis, or at least a slight crisis. I'm very curious though, since the natural sciences are mostly not the ones being criticized, if these scientists are saying, yeah, there's a reproducibility crisis over there in the social and behavioral sciences, or whether they would own up to the fact that there might be similar problems in their field. So I think, to me, the summary from this combination of sources of evidence, some of it empirical evidence about the threats to reproducibility, and some of it more logical arguments about the rules of NHST and how we've been misbehaving compared to what we should be doing if we want our p-values to be interpretable. So it's kind of a 1-2 punch. I think one is that we realize that common research practices like p-hacking and harking violate the rules of NHST and increase the rate of false positives, just as a matter of reasoning and logic. If we think through the consequences of these practices, it's inevitable that they will increase the rate of false positives and decrease the reproducibility of our work to the extent that we use these practices. And then the second punch was the empirical evidence that many published findings are difficult or impossible to replicate, whether that's 50% of published findings or smaller proportion or higher proportion. There's a lot of, again, of debate, but I think that most estimates are that there's more reproducibility problems than we would like. So I think my takeaway from this is that the published literature looks very nice. A lot of things are significant. You can get subtle effects to work with even relatively small samples. But the reality is that things are probably a lot messier and a lot uglier than that, that even the effects that are true in the literature are probably harder to get than the methods that we're used to get them a lot of the time. If we really want to get reliable and precise estimates of those effects, we probably need to use more intensive methods. So in thinking about what are the arguments for and against using more open and transparent methods, I would say the main argument against using more open and transparent methods is that if we don't p-hack and HARC, our results will be less pretty. And that might sound trivial, but it's actually a big problem because many journals only want to publish relatively neat, tidy, eye-catching, counterintuitive results. So I think that's a really big strike against using open methods. So arguments for open science, our values say that we should be open. The rules of NHST say that we need to be transparent about what was planned and what wasn't. If we don't do it, we may lose other people's trust in us. And I think that open science is necessary, but not sufficient, to make science self-correcting. And the main argument against it is that your results will be less pretty, and that has serious consequences for your ability to publish and advance in your career as the way that things are right now. Okay, so what about solutions? So I'm going to talk a little bit about some proposed solutions, and I'm going to spend the majority of the rest of the time talking about solutions at the individual researcher level. So what can we in our labs do? But I want to point out, and I have one slide at the end, that I actually think we should also be very focused on solutions to changes to the incentive structure, things that gatekeepers can do. It's just hard to give a talk about that, right? We can't really do much about that as individual scientists, so I'm going to talk about things that we can do starting today in our labs. But I do want to make sure that part of the discussion is about how we can change the incentive structure and what responsibilities gatekeepers and people in positions of power have to help with the solutions. So one theme running across many of the solutions proposed is that we need to remember that scientists are human, and we need to build a system for human scientists, not for the idealized, completely objective, rational scientists, which doesn't exist. So one way to put it is we want to live up to Merton's norms, or I'm assuming that we want to live up to Merton's norms. We might quibble with some of the details of Merton's norms, but assuming that we generally agree that these are good ideals for science, how do we design a system given that we're human, given that these things won't come naturally to us? Lack of hierarchy won't come naturally to us. Disinterestedness won't come naturally to us. Being comfortable and expecting others to criticize us and scrutinize our work and find errors, that's never going to feel good. So how do we build a system where those things are valued and incentivized despite the fact that they're not necessarily in our nature? So how do we keep humans honest? And again, this is not to say anything negative about scientists beyond just that they're susceptible to the same flaws as any other human. So one is the theme that I've been talking a lot about today is transparency. So what does that mean? That means things like making materials publicly available. Maybe that's even down to a video of your protocol, or for geoscientists, maybe it's actually making the rocks, samples of the rock publicly available or available to other scientists. It means sharing data whenever possible. So whatever data is necessary to reproduce the claims, or to test the claims in your paper, those should be made publicly available whenever possible. And there's a lot of situations where there are limits on that, mostly legal and ethical limits that are important. But the default should be that those are available. It means disclosing flexibility in data analysis, and along with that, distinguishing between what was predicted or planned and what wasn't. And this is what pre-registration, the aim of pre-registration, or one of the main aims. There's multiple reasons you might want to pre-register, but one of the main aims of pre-registration is for you and for others to know what was planned and what wasn't. So again, I'm stealing from Leif Nelson's slides here. What is pre-registration? It's deciding ahead of time how you're going to determine your sample size. So maybe you don't know, but you know your decision rule. You know that we will stop collecting data on July 1st, and that's how we determine our sample size. Deciding what your manipulations will be and all levels of each factor, your measures, your analytic strategy, and your critical hypothesis test. So you don't have to have a directional prediction, but you have to specify which analysis is your critical hypothesis test if you want to be doing hypothesis testing. Maybe you don't want to, but if you're going to claim to be doing hypothesis testing or want to interpret p-values, then you need to have that component. write that down, share it, and then collect data. So the ideal registration, it happens in that order. And so I don't do a lot of confirmatory research. I don't often have hypotheses. I do a lot of descriptive work with exploratory questions, but I'm still pre-registering now because I want to make sure that I'm not later tempted to claim that something was predicted. So even if not all of these things apply to you, maybe you don't have manipulations, maybe you don't have a critical hypothesis test, you can still pre-register that you don't have those things, and that helps you remember and others know that you were planning to always report it that way. One important fact about transparency, including pre-registration, but also sharing data, et cetera, is that transparency is not quality, right? Transparency doesn't guarantee credibility or quality or validity, but transparency allows others to evaluate the credibility of your claims. So it's possible to have transparently reported research and weak methods, right? But when it's transparently reported, others have a chance to identify the weaknesses in the methods. When it's not transparently reported, people can't tell. Again, going back to the used cars, they can't tell whether the engine is good or not, whether the methods or the data, the evidence is strong or not. Okay, so transparency is one, I think, really, really important component to helping us live up to these Mertonian norms. But there's another thing that goes hand in hand with transparency. So because the more transparent you are, the more you're opening yourself up to criticism, right? You're letting others find errors in your data, in your procedure. If you changed, what they call in medical research outcome switching, and so initially your key prediction was that your manipulation would affect this outcome, but actually you found that it affected that other outcome, and now that seems like obviously what you should have predicted and what the theory predicts and so on, but it keeps you honest about the fact that that wasn't your prediction from the beginning. So opening yourself up to that criticism, being more transparent means making it easier for others to catch you if you're wrong. So I think that if we want science to be as productive as possible, to accumulate knowledge as much as possible, then transparency needs to go hand in hand with higher standards for our methods, right? If we have transparency but we don't have high standards for our methods, it just means that we're putting less rigorous research out there, sure, it's great that it's transparent because then other people will be able to tell that it's less rigorous. What we really need is also high quality methods, not just transparent research. So what does that mean? So I want to emphasize that part of what this means is just all the things we teach in basic research methods and statistics courses to our undergraduate and graduate students. So it means construct validity, means internal validity, means external validity, statistical validity, et cetera. But some of the things that I think we've realized we need to do better on that we may have not been as good about as we should be, and again, I don't want to leave aside all the things that we've probably been doing quite well all along. Those are important too. But some things I think we need to do better on are increasing our sample size in psychology, but really the goal here is to increase precision, power if you're in the NHST framework, but in any statistical framework you want to have precision. So whether it's a null effect, you want to be able to estimate that precisely. If it's a real effect, you want to be able to estimate that precisely and really be sure that it's not a null effect, et cetera. Why are large samples better? I probably don't need to tell this crowd, but here's a really simple illustration of why large samples lead to more precision. So this is a simulation where we're estimating a mean from a sample of 5. So every time the red bar moves, it's a different estimate from a different sample of 5. And so here you see that that red bar, the mean, is jumping around quite a bit around the true value of 10. And that's what happens when we have small samples. If we go up to 50, the red bar is jumping around less. And then if we go up to 1,000 per sample, we're getting a really precise estimate almost every time. Precise and accurate in this case, assuming that there's no systematic bias. So large samples help with precision. Of course, you can have a large sample and systematic bias or bad methods. That's not going to solve that problem. Another, I think, kind of high standard that we've now realized we should be paying more attention to, or at least I think so, is making sure that we have small p-values when we're making strong claims, and that when we see high p-values, especially in the absence of pre-registration, when we're not sure that the rules of NHST were followed, then high p-values close to 0.05, are less strong evidence. I know I'm mixing hypothesis testing and other kinds of ways of interpreting evidence in ways that are not completely kosher, but given that we don't always know everything that went into producing a p-value, we've now learned that there are reasons to be less sure when the p-value is higher or closer to 0.05. And it took me a long time to wrap my head around this. It didn't seem intuitive to me that a 0.04 is less strong evidence than a 0.004. And so I was working this out and sketching it out. And so I'll go through the thought process with you in the hopes that maybe it'll help other people kind of wrap their heads around this. So I think one of the reasons it seems counterintuitive is when we're doing null hypothesis significance testing, we're thinking in terms of the null distribution, right? Null hypothesis significance testing starts with the assumption that the null hypothesis is true, which is weird because we don't really believe that, but that's what a p-value is based on. To interpret a p-value, you start with the assumption that the null hypothesis is true. You calculate how extreme is your result under that assumption. So you have a distribution of what the results would look like if you ran the study over and over again. If the true effect is 0, you would get a distribution of results like this. And if you get an extreme enough result, if your particular study that you actually did run gets a result that's extreme in this distribution, and namely that's in the 5% most extreme parts of the area under the curve, then you reject the null. You say the probability that I would get a result this extreme or more extreme if the null were true, or assuming the null is true, is small enough that I'm going to reject the hypothesis that my result came from this distribution. So when we think about it this way, if we look at the null distribution, it seems intuitive that we're going to get results close to the threshold pretty often, at least as often as results further out from the threshold. So the threshold for significance would correspond to a p-value just below 0.05. And when we look at this distribution, it looks, yeah, like, sure, we're going to land just past that threshold quite often. But remember that when we're getting a significant result, we're rejecting the idea that we drew from this distribution. And we're instead saying, no, I've now rejected the null, so indirectly I've provided support for my alternative hypothesis, or the idea that I was drawing my result from this other distribution, not from the null distribution. And I've drawn it arbitrarily far away from the null, but remember, these are distributions of results from entire studies. So they actually do look quite far apart when you do simulations of what the distribution would look like under the null versus under a moderate effect size. The distributions don't overlap a ton. So if we really were drawing from this alternative distribution, we would be getting results out here quite often, which correspond to very small p-values under the null. And if you think about what the distribution of these results look like when we convert them to p-values under the null, they're actually mostly very extreme p-values, very close to 0. And in fact, we can simulate this and graph it, and there's a Shiny app for that. And I have the URL down here. So if we can change the effect size and the sample size, so we can mess with the power and see what this looks like under different levels of power. Here's the curve for 80% power. So when we have 80% power, 80% of our results are going to be below 0.05, and 20% are going to be above 0.05. And within that proportion that are significant, within those 80% of p-values that are significant, I've asked it to calculate what proportion out of all the p-values are between 0.01 and 0.05. In that shaded area, that's 20% of all our results. So 20% are non-significant. Another 20% are between 0.01 and 0.05. That leaves 60% of p-values will be less than 0.01. So if you run a study with 80% power, you have a 4 in 5 chance of getting a significant result, and 3 out of those 5 will be very small p-values, or less than 0.01. So the distribution of p-values when there really is an effect should be right skewed. If you ran the study over and over again, you should get p-values very close to 0 a lot more often than you get p-values very close to 0.05. It's less heavily right skewed when power is lower, but it's always right skewed. It's always the case that you have at least a 2 to 1 chance of getting a p-value below 0.01 compared to between 0.01 and 0.05. So if you're running 3 or 4 studies and getting p-values between 0.01 and 0.05, that's a sign that you're maybe not coming about those p-values completely legitly. You might be p-hacking without realizing it, because getting 3 times in a row in that 20% area is not super likely if you're drawing from this distribution of very right-skewed p-values. So that doesn't mean that we shouldn't trust any results where the p-values are high, but that we should draw less strong conclusions. We should be less confident if we're not consistently getting results with p-values close to 0. And in fact, the idea of null hypothesis significance testing was always about long-run trends, right? So we should, if an effect is real, we should be able to consistently get it, and the distribution of p-values should look right-skewed. right? And that's really how we should build up confidence in a result, is by looking at long-run trends, making sure we can reliably get an effect, and making sure the pattern of results looks like what it would under the alternative distribution. And then another way to have high standards to make sure that you're not putting out transparently reported research that's not going to be rigorous, it's not going to hold up over time, is to replicate effects before having too much confidence in them. Again, I think it's worth putting stuff out there before we know if it can be replicated, but we should calibrate our confidence in it. So we should be more confident to the extent that we know we can get it over and over again. But I want to put a caveat on this replication. I think that in psychology, many of us thought that we were replicating effects. We were putting 3 or 4 or 5 studies together, or publishing many papers all pointing to the same general phenomenon. And that still didn't guarantee that the phenomenon was real. In some cases, we still ended up not being able to replicate those phenomena. So what happened? We thought we were replicating and we weren't. One example is the facial feedback study that was in a lot of textbooks, and then there was large-scale pre-registered replication that failed to find it. I've heard there's a follow-up study now looking at a potential moderator. But it's not the only example. There's ego depletion, there's professor priming, and so on. Many of these were built on dozens of studies or more across dozens of papers and dozens of labs. So I think it's important to remember that replications can have some of the same downsides as original studies, and so we want to make sure that we have high standards for replications as well. So they should be transparently reported, pre-registered whenever possible, have a large sample, and have small p-values over the long run. So I think replication helps us have more confidence in a result to the extent that replications, just like original studies, have some of these other desirable characteristics. Okay, so to summarize, I think that one of the fundamental goals of science is that we want credibility. We want our claims to be calibrated. When we have confidence, we want to have the high chance of being right. We want to make sure that we're not leaping to strong conclusions without strong evidence. I think being open and transparent is critical to credibility. It's a necessary condition for credibility, but it's not sufficient. It doesn't guarantee credibility. Being open and transparent allows others to evaluate our work and assess whether our claims are credible, but we also need high standards because otherwise it's just going to allow others to see that our claims are not very credible or that our evidence is not very strong. So I think transparency and high standards go together to help build up credibility. So I want to add a little postscript, which is that I've focused most of this talk on what individual researchers can do. We can be transparent to let others verify our claims, find out if we were wrong, and we can be skeptical, make sure that we don't get too confident in our claims too soon without enough evidence. But as I mentioned, I actually think a lot of the conversation should also be around what gatekeepers can do, so what journals or societies or universities or funding agencies can do. And I have some ideas about that, but I'd be curious to hear your thoughts as well. So I think that what people in positions of authority in these kinds of organizations, what they can do is also value credibility, and value credibility above things like impact, status, novelty, etc. And what that means concretely, it means that I think journals should be open to publishing null results, quote unquote boring results, not all boring results. I think there are some arguments to be made for the importance of a research question being interesting enough to be worth studying, being willing to publish replications, errata, critical commentaries, etc. I think that those institutions themselves should be transparent. So journals and societies and universities and funding agencies should be transparent about their process, and especially I think about conflicts of interest. One of my big pet peeves is status bias in the peer review process. I think conflicts of interest come up a lot more than I think we admit in the peer review process. I think we need to be more proactive about that and transparent about what we're doing to counter that. And be accountable. I think that we should want to test ourselves, whether we're running a journal or a society or a tenure and promotion committee or a grant panel, etc. We should want to see if the things that we endorse and publish stand up to post-publication peer review. That's what I mean by PPPR. We should welcome that kind of scrutiny for our products. Maybe we should even actively seek it out. We should do self-audits, ask people to try to criticize or replicate or analyze with forensic tools what we've published and see, does it look credible from a skeptical point of view. So I've often thought about how in high-stakes situations like airport security, I actually don't know, I should find out, that there are audits done where maybe people, where the TSA agents are tested to see if they can detect planted things that look like bombs. And I think we could do the same thing with journals or other kinds of grants and so on, see if the system can detect things that are intentionally not sound. I would want to know, if I was running a journal, I would want to know, are we catching many, not all, we could never catch all of them, but are we catching many of the things where people expect us to be catching? Are the things we're letting through as sound as we would like them to be, and so on. And there are a lot of organizations, journals, societies, et cetera, who are making great strides in these ways. The latest one I heard about was the Southern Methodist University Psychology Department just put out an open science statement saying that they value transparency and open science and that it will be part of their evaluation criteria for hiring and promotion and so on. And then plenty of others. I'm affiliated with some of these, full disclosure. One I'll point out is the Society for the Improvement of Psychological Science, which I founded with Brian Nozick. And we have our third meeting this summer if anyone's interested. We're very open to people from other disciplines also coming. You can find the mission statement on our website, but the idea is just to try to work productively to create tools and resources for people who want to do more open and reproducible science, to focus on trying to build more rigorous and more transparent science. The official journal of the Society for the Improvement of Psychological Science is Collabora Psychology. And the mission statement of that journal says that they check for rigorously and transparently conducted, statistically sound, adequately powered, and fairly analyzed research, and that we don't try to predict the impact to the field ahead of time. So it's more focused on rigor rather than things that are hard to anticipate, like impact. So that's it. I'll leave it there. Thank you.
This was really interesting, and I agree with pretty much all of the recommendations that you made. But so, in this audience in particular, a lot of us are anthropologists or evolutionary psychologists who also do field work, and there's another trend that's been going on in psychology, which is to kind of challenge some of the dominance of conducting studies with university student populations, and a push toward trying to do more cross-cultural kind of research. And that's challenging for a lot of the things that you raise, because when you go into the field and you're doing some kind of an experiment, you often encounter small sample sizes, and you also have a lot of barriers to replication. And so it seems like that puts a greater burden on those of us who do that kind of research to do things like pre-register, even though I think we've actually been slower on that curve than a lot of other psychologists. But I'm wondering if you have other kind of suggestions or thoughts about how to sort of bring together those two trends.
Yeah, I have a lot of thoughts about it, partly because the research I do myself is quite intensive, so it takes us like 5 to 10 years to run a study. We do a lot of behavior coding. One argument I would make, just speaking for myself, is that given how hard it is for me to run a study and to collect data, I want to be all the more sure that I'm not letting myself be susceptible to biases. So I want to try to make sure that I'm engaging in as many of these practices as I can. Some of them won't be possible. Like, large samples are a lot harder if you have intensive data or hard to reach populations and so on. That's all the more reason to do the other things that you can do to make sure that if the evidence is coming in bits and pieces very rarely, if there's bias in that evidence, those biases are going to persist for much longer. So I think we want to try to remove as much bias as we can through things like sharing the data, so if there is a problem, other people are more likely to detect it, through pre-registration, et cetera. The other thing I would say is I think one of the reasons I've started talking about it as a credibility issue is that brings back in a lot of the basic values of validity that we've always had, or at least give lip service to the idea of having representative or at least diverse samples, having rigorous methods, not just relying on the most convenient methods, not doing everything on MTurk. We've always talked about valuing those things, and that if we want credibility, if we want to make claims about people in general, we should be studying people in general, not just undergraduates in the US. So I want to kind of broaden the discussion to be not just about does it replicate, but does it mean what you say it means. Part of being credible is making a claim that is supported by the evidence. If your evidence is narrow, just focused on college students or MTurkers, then your claim should be narrow. So I think by broadening the conversation, I think we can try to bring those issues back in and kind of marry them to the reproducibility issues. I think doing that together will help defray some of the downside. So requiring larger samples, et cetera, I do think is harder for some kinds of research than others, but often those kinds of research have other advantages over the MTUR studies and so on. So I think it all needs to be part of the evaluation and part of the conversation. So that we're saying on one hand, you get a smaller sample, we can't avoid the fact that that means larger error bars. That's just a mathematical fact. On the other hand, you had a sample that's not represented in the literature, and so we can learn the uncertain knowledge that we gain from that sample is really, really valuable despite its imprecision and despite the uncertainty around it. So I think, yeah, having that conversation in a broader context will be helpful for that. I had other thoughts, but I can't remember them. Maybe they'll come back. Let's see. Keep talking. Yeah.
Thank you for a really thought-provoking talk. Really great advice, I think. I was wondering whether you had any advice or thoughts about qualitative research.
I don't know very much about qualitative research. So in my own research, we have, recordings of conversations and so on, but we always turn them into quantitative data. So I'm not sure what people mean when they talk about qualitative research, other than the little bit of experience I have, which is quickly turns quantitative. But I know it's one of the topics that some people in the replicability or open science movement are talking about, how to kind of create standards and norms for qualitative research, but I don't have a good answer. I know it's part of the conversation, but not. I think we're not as far along with those kinds of practices.
I have a follow-up, another quick question. I once heard a talk by an editor-in-chief of a chemistry journal about research ethics, and she shared some data with the group about who it is who commits any sort of publishing-related ethical violations. And the vast majority, at least of the sample of violators, were the earliest career people, which were students mostly. Whereas I think a lot of us conceive of these super powerful, high on the hierarchy, like cutting corners because they're just, too powerful to have to follow the rules kind of people. And it just flipped on its head what my assumption had been, I guess, or what my prediction would have been. I was just wondering whether you have any thoughts about I guess that has to do with incentive structures or time frames and expectations.
I mean, I could try to come up with some explanations on the spot, but they would be completely post hoc. I mean, I think the great thing about that is just the idea that we are collecting data on that. I think we really don't know, and I think we need more meta-science to understand, because if we know descriptively who's committing more of these acts, then we might have a better idea of what are the reasons for it. It could be that early career people, there's a broader range, and so the extremes are going to be more common among early career people than later career people. So if you take any extreme behavior, it's going to be more common when there's a broader range of people and there hasn't been as much selection on the population yet. That's my first explanation, but I'm not sure if it's... Yeah.
So I have a few questions, but I'll ask a simple one first. So assuming that humans like novelty and we like simple answers, it seems like there's going to be always a push for significant results and easy theories to explain those significant results. So it seems like the people who pre-register might put themselves in a disadvantage because they're less likely to get those results. Thus they're less likely to publish, which will lead to less jobs, less grants. So it seems like if you take almost like an evolutionary point of view, the people who will populate academia are the ones who don't do this because they're the ones who are more likely to publish and give us those very great stories that we all love.
Yeah, so this argument in the Natural Selection of Bad Science paper, and I buy it. So my own views about this have evolved. I used to be part of the group that thinks we need, incremental change and we need nudges, and it's fine for things to be optional and whoever wants to do them can do them and so on. And now, partly because of my role editing papers and reviewing papers and so on, I think we're at the point, at least in psychology, where many of these practices need to become the default, and you need to have a good reason not to do them. And again, there are good reasons not to do them, but what I'm seeing happening is exactly what you're describing, where someone, take paper A and paper B. Paper A is pre-registered or has open data. In either of those and many other practices, leave you open to people finding out what's wrong with your study, et cetera. So if you register, people can see that the pattern of results you observed is not what you predicted. Or if you share your data, people can see that the effect is being driven by an outlier or something like that. And I've seen cases where reviewers will reanalyze the data or will look at the pre-registration very carefully and will point out that actually the claim you're making is not justified by the data or by the pre-registration. And then we're in a position where we're like, well, we have to hold that against the authors. So then the question is, what do we do for paper B where we don't know that? We don't know what was planned a priori. We don't know if the data are normally distributed or have any kind of problems and so on because the data aren't open. So we have the option of either assuming everything's fine with paper B, which is unfair to paper A, because basically we're saying if you don't tell us, we're going to assume it's fine, so then why should you tell us? Or assuming everything is not fine in paper B, which is not fair to paper B. So I think we're in a really difficult position if it's completely up to the authors whether to do this or not. The incentives are not there for the authors, and it's not fair, I think, to ask people to do this if we're letting everyone who doesn't do it completely off the hook and treating their paper as if they had pre-registered and shared their data, everything would have looked totally kosher. So I'm moving more in the direction of I think these things should be the default. I think it should be a point against you if you don't do them when you could have. Now, when you couldn't have, so secondary data analysis, you can't pre-register, proprietary data you can't share, re-identification risk could prevent shareability, et cetera. I think we need to think very, very carefully and very hard about how to deal with those cases. But in the cases where people are on equal footing, both papers could have been pre-registered or the data could have been shared, it's very difficult to know how to not penalize the people who are doing a more open and transparent thing. So yeah, I don't really have an answer other than I agree that it's a problem.
And then another thing which you didn't address was the publication bias. So obviously, we run a lot of our results and only publish some set. Mm-hmm. Let's say we pre-register all those results, mm-hmm. and 10 people tried to do the exact same study I did, yeah. but somewhere else, and my results came out significant, but for them it didn't come out significant. It could be that this is a publication bias, but it could also be that they're just not doing it correctly. Is there any good solution on pre-registration is great, but it won't deal with this publication bias?
Yeah, the short answer is registered reports, which is where before you collect the data, you have your pre-registration, you have your description, your rationale, so you write your introduction, you write up the method section, you write your planned analyses in the results section, you submit that to a journal, and that goes out for peer review. And if the editor and reviewers think that the question is interesting, the design is solid, it's worth knowing the answer, then they give you an in-principle acceptance, and the results get published regardless of the outcome, assuming that you meet some validity checks in the data. So there's now 97 journals that do this across different fields. Not the most prestigious ones for the most part, but there are more and more that are doing it, that are offering as one type of submission. So that would get rid of publication bias, assuming the authors don't pull out if it doesn't come out. The other thing I would say about so the different part of your question is how do we know if some people get it and other people don't, how do we know if that's just sampling error or if that's like the people who get it have some kind of expertise or skill that others lack? I think we need to make that decision independent of the outcome of the study. So we need to build in validity checks or ways to assess the quality of the study independent of whether the key result is significant or not. We can't make that the criterion for deciding if the methods or procedures were good. So we need to think harder about validity checks. We need to think harder about what we need the authors to report in order for us to evaluate whether the procedures and methods and stuff were strong. I think it'll be a good thing to start thinking through those questions. If we can't use the p-value to decide if the study was well run, what can we use? What do we need to know? Yeah, I think you had a question.
Well, so I apologize to whoever wrote this paper because I don't remember their name. Someone was talking about essentially structural things we can do to motivate some things like perhaps requiring students to do a meta-analysis before receiving their master's or something like that, or and how like motivating people to do replication studies. I just wondering if you could speak more on that.
I think that I'm not against having replication be part of training, but I think that it should be up to people with job security to take the hits first. So as much as I admire all the early career people who are doing things transparently and openly, that's awesome. I think they deserve a lot of credit, but they shouldn't bear the responsibility for taking the lead on doing those things. So I would prefer solutions where the burden falls on people who have tenure and have jobs.
So same thing for replications and meta-analyses?
Yeah, I mean, meta-analysis is a whole other can of worms. I have a lot of thoughts on meta-analysis. I don't think it does what we think it does.
Cool. Let's talk to you more about that, and cool presentation, by the way.
Thanks.
Sorry, I have a follow-up question,
Sure.
if possible. So For people who do the type of work where you're going into the field and supposedly collecting something that's gonna like get you a certain ways, essentially, I'm wondering about the incentive structure, kind of what Brooke was saying for doing that type of work, especially if someone can just, you know, if you share everything, and they can just use that data, generate their own stuff, sets up a different incentive structure. And I guess the question would be, what's the happy medium for how long you can hold on to your data? It doesn't depend on the type of data.
Yeah, so that's something I've thought a lot about, because so like my last study, we're like 8 years into the coding now, and we still have several more years of coding. And so my reactions have changed over time. So initially I was like, there's no way I'm sharing these data with other people. They were so precious and so hard to get. I need, my future graduate students are going to be publishing off of these data. Their livelihood and success depends on us being able to continue to mine the data for stuff. That's still all true. So the baby step we took was when we publish a result off of a data set like that, we make the variables necessary to reproduce our results publicly available. So we make like those, 8 columns out of the 10,000 in the data set publicly available. We've also made our codebook publicly available so people can see everything that we measured and when we measured it and how we measured it and so on, so that at least that part is transparent even if they can't access the data. But I've come to be, I'm not quite ready to post my data completely publicly, but I think I'm going to get there, just paying attention to my own evolution. I'm starting to realize that a lot of my concerns were probably overblown, so this idea that people would immediately jump on my data and do what I was planning to do with it, that doesn't seem to be what's happening when I get contacted by people who see our codebook and are interested in using our data. So I've now tried to advertise that the codebook exists. If people want to use our data for something, they should contact me, and we reserve the right, if it's something we were planning on doing, to either say, no, we're going to do that, or to invite you to collaborate with us. But most of the requests I get are not things I was planning to do with the data, so it's actually kind of cool. It's, these precious, hard to collect data people are getting more value out of them than if I hadn't given others the opportunity to use them. And when it is similar to what we're doing, often we'll be happy to collaborate because the other team adds something new. And in the cases where we're like, no, we're already halfway through that project, we're going to do that. Sorry, I don't think it leads to too much bad feelings. But I think that in general, there's people like me think a lot about the potential downsides of sharing, but there's actually a lot of potential upsides. So now when someone approaches us about collaborating, they often have a very different research question, and that's cool. It forms a new collaboration. I often learn a lot. Plus, we also tell them that they shouldn't run their analysis until they've found 4 errors in our data set. So we've caught a lot of errors that we wouldn't have otherwise caught. So there's all these like side benefits that I hadn't anticipated, and there's some evidence that papers with open data get cited more and have more impact than papers that don't have open data, so actually it brings more attention to your work potentially. Okay. But I do think we need to take seriously, like it is a model for many labs, including mine, that we're going to keep publishing off of one data set for a long time, and it could be terrible if we were scooped. I think the probability of being scooped is a lot lower than we think it is, but so it's something I think we should be taking.
Very encouraging. Thank you for the cool down.
So a lot to chew on. Thank you. I wanted to go back to the norms component that you mentioned at the beginning and present maybe an anthropological perspective. And I don't mean the sociology of the anthropology, but instead looking at the issues through the lens of an anthropologist. So you've spoken repeatedly about incentives and the incentive structure of existing career and publishing components, and other people have published on those. I have no disagreements with any of that, and I think people do respond to incentives. But the reason we don't have more fistfights at academic meetings is not because of incentive structures in a simple way, right? That is, most of what humans do, that is, it is about incentives, but it isn't about incentives the way you've been using that word and the way most people in this question of replicability are using it. So most of what people do is not enforced by direct punishment and direct payoff, right? It's mostly enforced through an understanding of the cultural norms. Right? So you said the norm of skepticism is important, right? And there are a bunch of ways we can approach that, right? So one is to say we're going to build hard incentives into the system so people get rewarded for challenging orthodoxy and publishing failures to replicate and so on. And that's, as I said, I have no beef with that. I mean, that's all good. But another way is to say, what are the mostly implicit cultural norms about the behavior of scientists on an ordinary basis, right? The sort of quotidian culture of science, as opposed to the hard institutional structures within which people operate. So you can say, that skepticism is a valued good in its end, on its own merits, right? And some disciplines do that more than others, but then there are different sort of meta-norms about that. So in economics, for example, this sort of aggressive skepticism is culturally valued in a way that is often shocking to, say, sociologists or anthropologists or psychologists, right? You're interrupting that guy's talk. What are you doing, right? Why are you challenging him on every detail, right? That's a cultural norm of valuing skepticism, but in some ways it's kind of counterproductive given the problem that we face right now, because it makes it about, it makes ownership of the idea itself the thing that is being challenged, right? So your work is bad because I'm criticizing, right? As opposed to another cultural framing of skepticism, which says, oh, this is a collective enterprise. This isn't an individually competitive market, right? We're all trying to find out how the world is. And so if you have a good criticism of my work, I thank you for that. And I say, I didn't think of that. I need to think about that some more, right? Which is not the norm in economics, right? The norm in economics is you go down fighting, right? And it's, because the go down fighting norm just leads to lawyerly argument. It doesn't lead to better knowledge in itself, right? I mean, it relies on a kind of, capitalist, it'll all work out in the end model. And obviously we see the consequences of that. So, I mean, I think part of what needs to happen is we need to socialize people differently so that their responses to criticism are not, oh, you're attacking me when you're attacking my idea. Right?
Yeah, I completely agree. That ideal of like, oh, you're criticizing me, that's flattering. That means you care enough to criticize and you're helping me, so I'm benefiting from it. I would love for that to be the norm in terms of, but I don't think it is. So I agree with that the economics norm is not the one I want, but I don't think it's the case that the ideal norm is the one that's present. I don't think it's the only alternative, right? I think currently in many fields the norm is that after publication, if you criticize something, it is a personal attack. So I don't know how to change that, but I do think, so one idea, and I do this now in my undergrad research methods class, is to teach Merton's norms and to say that really if you're aspiring to be a scientist, we should be aspiring to these things and to try to train ourselves to react that way to criticism among all the other things. So I think teaching that that's a value is one step, but I don't know how else.
I think moral exemplars are a good way of, so we, if we tell the myth or the legend of the admirable moral exemplar. So I probably got the details wrong because I'm turning what was, I think, a fact into a myth. But I think it was John Maynard Smith who at some point gave a talk, and some smart-ass graduate student stood up in the back and said, this is inconsistent with what you said earlier, right? In a previous publication, right? And his response was, yeah, well, I changed my mind because that's what the facts dictated. What do you do when the facts dictate that you were wrong, right? I mean, if we tell the story of the people who didn't go down fighting, but the people who said, oh yeah, I embraced the criticism, then that's one way of socializing. Just on the board is great, and teaching students that. But it's not clear whether the outcome of that is the economics model or the John Maynard Smith model.
That's a good point. Yeah, that's a really good point. Thanks.
I meant that very constructive.
Yeah, no, I'm very glad for constructive criticism.
Thank you. So your discussion about the statistical issues was all framed in terms of null hypothesis and necessity. Do you have, is doing Bayesian statistics worth the trouble? Does it address these questions, or is it just?
I'm no expert at all on this. I'll tell you my opinion after having listened to the Bayesian versus frequentist debate without any particular expertise in it. My impression is that maybe the Bayesian approach is better. I'm leaning towards that conclusion, but not for these reasons. I think it might just be a better statistical approach for other reasons, but I don't think it solves any of these problems. I think the only way in which it's slightly better on these dimensions of like credibility, reproducibility, et cetera, is that it happens to be the case, and maybe that's not maybe there's a reason for this, but right now, the people, at least in psychology in the Bayesian community, part of their ethos is to embrace uncertainty and to avoid strong claims without strong evidence and so on. But I don't see anything inherent to the Bayesian approach that makes that more the case in a Bayesian approach than a frequentist approach. So you could take a Bayesian approach and make it dichotomous. You could take a frequentist approach and make it not dichotomous. You could have humility in a frequentist approach. You could have humility in a Bayesian approach. I think it happens to be the case right now that Bayesians are putting more of a premium on calibration and humility and so on. My guess is if Bayesian approaches became the default and were trained and taught in the mass ways that frequentist approaches are, they'll get diluted and turned into dichotomous things too. So I'm considering switching to Bayesian framework, but not because I think it solves these problems. So I don't mean to say I don't think that Bayesian approaches are better than frequentists. They might be, but if they are, I don't think it's for these reasons. That's my best guess. Yeah.
I want to come back to your idea about credibility. Your focus in the talk has been on statistical and other kinds of credibility. And it's very valuable. Two other kinds of credibility crises are the absence of mixed methods in research, the multi-trait, multi-method problem. It is routine, and even in the studies you're talking about, to use a single method, a scale. And yet from Campbell on, we know that methods variance is a huge part of the variance you're trying to account for in the first place. The second is the problem of sampling, which is if you only sample undergraduates in your class, and not everyone does, there's a generalizability problem, a believability problem, which relates to credibility. And it's a deep problem. And so what are your thoughts on broadening this topic? Because if your goal is credibility, wouldn't these things have to be a part of your talk?
Yes, absolutely. And that's why I started changing the language to be about credibility rather than just replicability. Replicability is just about statistical validity. If I do the same thing, will I get, is it sampling error or is it a true signal, right? And that's one kind of validity. But it's weird that it's taken me like 5 years of repeating this to undergrads over and over again. There's construct validity, there's internal validity, there's external validity, there's statistical validity. And I started realizing like, oh yeah, like the replicability movement is so focused on statistical validity because I think we identified a huge problem in that area that we were completely blind to, or at least I was before. So I think there's a reason why all of the focus is there right now, but I think we need to take a step back and say, well, if our goal is validity more broadly or credibility more broadly, then we need to join up with the people pushing for more external validity, or, I mean, even internal validity. I think there's huge problems that we're not thinking about. And certainly construct, my favorite has always been construct. My own research is, the reason my research takes so long is we get self-reports, peer reports, and real-world behavior. So we put recorders on people, they wear them for a week, and we have 6 coders per participant code their behavior from the audio recordings. So it's very near and dear to my heart that we should, that a measure is the construct plus the operationalization, and we need to think about that. So I would love for all the people pushing for all those different kinds of validity to join up and say these are all related to credibility. When we make a scientific claim, we're putting all of those on the line. We're saying we're prepared to defend the construct validity, we're prepared to defend the generalizability to the extent that we're claiming that it's generalizable, and so on. So I think there's a lot more in common among those groups that are pushing for those different things than there is difference. Part of it is priorities, right? And so there's a little bit of debate about when there's a trade-off, what should we prioritize? I think that's interesting to think about too. But really all of those are necessary for credibility.
Okay, well, I'm afraid we're all out of time. So